right, everybody, welcome to physics. So as I stand here walking the plank on my little 2x4, it's actually I think a 2x3, as on my little board here, you can see that, that I'm not falling down. My balance is at the moment average at best, I guess, but I'm not falling. And so what that means is I have currently balanced forces. Force of gravity is pulling me down, and I'm not falling to the ground because I'm getting a normal force from this plank of wood underneath my feet. But what is it? Whoa! Man, failure. What is it that is giving me the upward normal force? Yes, it's the block of wood, it's the plank, but what gives us this upward push? And the fact that you can see the flexing of this plank as I stand on it gives us a little bit of a hint as to what it is that is giving us this upward support force. And so the question is, what is it? So we'll use this idea of the wood flexing, and the more I hop up and down, you can see more flexing. Hope this thing doesn't snap, right? What I can also do is I can add a second plank. So if I were to add, it's frozen. If I were to add a second plank and kind of spread my feet across, not only does it give me a little bit more balance because I've got a wider spot for my foot, but if we were to look at those images, if I try and balance equally on both as much as I can. So if we were to look at a side-by-side of the two images of our boards, what I should be seeing is that I don't have as much flexing in the two-board system as I do in the one-board system. So again, this hopefully can lead us down the path of what is it that actually gives us a normal force and what affects that normal force. In addition to that, what about stepping on a bathroom scale? What if I step on a bathroom scale, I end up with this upward push from the scale? What if it's me and another object? My little Santa Pez dispenser. Well, if I stand on top of my bathroom scale, it's going to give me a reading. Well, what happens if I take this Pez dispenser and I set it right alongside? Well, now I have an upward support force for me and for the Pez dispenser. What happens if I jump off the scale extra quick, leaving nothing but the Pez dispenser on my bathroom scale? Is that going to somehow give me this added upward force? Not me. Is this going to give the Pez dispenser some added upward push, therefore throwing it in the air? Let's take a look. All right, so it looks like the Pez dispenser was safe. So how is it that the normal force knows to stop pushing? I jump off, and somehow the bathroom scale knows to stop pushing so hard. That way, the Pez dispenser doesn't get launched into the air. So what is the normal force? What does it come from? And how is it so smart? How does it know not to throw the Pez dispenser in the air? And then as soon as I jump on there again, I don't know if I can jump on there. As soon as I jump on there again, and just like that, it's now supporting my weight again. How does it know to do that? So all of these questions can be answered by looking at the normal force in a way that we typically refer to as the spring model. So if I have my spring right here, we know that if we were to place a spring on a tabletop, I place my hand on top of it, right? So if I kind of take a look here as I press down, I know that the harder I press, the further down I'm going to compress that spring. If my hand is stationary, I have equilibrium, I have balanced forces. So that means that as I push down, I am going to experience more upward force, a little harder, more upward force, and so on. So what we're going to do is we're going to look at the solid materials. A normal force is a force that comes out of a surface, so it's directed outward, and it is perpendicular to that surface. The word normal is a mathematical term that actually means perpendicular. So we're going to look at solids. Any force coming from a liquid or from a gas or fluid is not a normal force. Normal forces come from solids only. So we're going to look at solids as a spring model. So we're going to look at it as if all of our atoms were connected to springs. So we'll take a look at that a little bit later. What I want to do first is a few demonstrations that kind of show us just exactly how how our spring model works. Essentially, if you were to envision all of your atoms in a solid connected in some kind of a grid, some kind of a lattice, if you were to envision them as if they were connected by springs, which I always remind people, they're not connected by springs, but they behave as if they do. So if I have a bunch of atoms, a bunch of tiny little solid items connected to all the other solid items with a spring, what would happen if I started to push in and I started to compress those springs? Well, those springs, they're going to push back because we know that's how springs work, right? If I take my hand away, it pushes right back to its original shape, push down again, and again, I can compress that. So if we look at everything as all solids as atoms connected by springs, we are going to be able to understand how the normal force behaves the way it does. I always call it the lazy force. It only pushes as hard as it has to. If it doesn't have to push that hard, it won't. So spring model is what we're going to use. So my first example here is going to be simply using a meter stick. Right? Any solid object has the ability to be deformed, change the shape. Some things can deform a lot. Some things can deform just a little bit. Think about how much deformation my spring has. Think about how long it is. And then when I smash it down, in terms of a percentage, I have just changed it by a drastic amount, but it's able to regain its original shape. That's what solids do. They can change their shape and then regain that original shape. There is this natural push to regain the original shape unless you push it so far that you permanently make a change by either breaking something or bending something. So before we get to that point, we have a solid that is changing shape and going right back to the original. Now, every solid acts this way, but it might not be so obvious every single time. So here I have my meter stick. And meter sticks can deform rather easily because it's a long, thin piece of wood. We have experience with that in our everyday lives, perhaps. But if not, taking a look at my meter stick, I can flex this meter stick. So I can deform that meter stick. And I know that if I deform it too much, it's going to break. So I have a limit as to how much I want to deform it. This is what gives us our normal force. So if I were to take a couple supports, place my meter stick across, something like that right there ought to work, something like this. And then what I'm going to do is I'm going to take my AP Physics book, my college physics book from forever ago, and I place it right on here, and what we're going to notice is some flex, some bending. I can see the actual bending in my meter stick. It's that bending, that shape change. This meter stick naturally pushes back to go back to its original shape, which gives me my normal force. My book has balanced forces. If I were to take a second meter stick and place it right next to it and place my book on top, all right, I still see a little bit of flex. Not as much, though, because my book is causing two objects to deform. Since I have two objects deforming, two objects push up, and so the amount of deformation I get is a little bit less. And so this now gives me the same upward push to cancel out the weight, the force of gravity, but I don't need as much bend. And if I had another meter stick and another meter stick and another meter stick, I can make an entire table, which is what a table is, right? Just a long section of wood. It flexes. Now, it might flex to the point. What happens if I flip it this way and this way? From our experience, we probably know, these boxes are a little bit bent up. From our experience, we probably are aware that when you have something aligned this way, it doesn't bend so easily. It might not even bend enough to actually be seen by the naked eye. So if I place my book right there, what's happening is the molecules or the atoms are being smashed together. They are flexing just like a spring, even if it's not enough where I can see it. And what happens? It gives me some upward push. So again, I can't quite see the bending of my meter stick, but I know that it's there. I know that it's happening. We can see this in other examples as well. So if I take my meter sticks and move them out of the way, take my supports and move them out of the way, what I have here is just a piece of foam, right? Foam, we know foam has the ability to change shape a lot and bounce back to its original shape, almost like a spring. So if I take a real close look at my foam and I place my book on the foam, you can see that that foam is deforming. It deforms more and more and more until we get to the point where it has deformed so much that it has enough pushback to cancel out the book. If I place my hand on top of the book and push down a little bit harder, I deform the foam even more. Again, we do have the ability to deform something so much that we end up with a permanent shape change. So this little piece of particle board right here, I know that if I were to bend this and bend this and bend this, eventually I get to a point where it no longer has the ability to bend and we get a permanent change. I have broken this. I can imagine a book sitting on here snapping this. Every solid object has a limit as to how much shape change it can undergo. Some things can undergo a lot. I can smash this down and it bounces right back. If I were to stretch it out, it goes back as well. Can I stretch it too much? Yeah, and the metal starts to bend. Some materials require a lot of force to actually get a shape change. Think a piece of steel. Push down on a piece of steel, you don't see any bending. But there is, at the atomic molecular level, there is some deformation in the arrangement of your atoms, as if they were connected by springs. They're not, but they behave as they are. So our normal force pushes back with as much strength as needed. Now, the example that we looked at was, how is it that my normal force knows how to change? Well, of course it doesn't know how to change. It doesn't know to change because it's not a living, breathing entity. It's just a meter stick at this point, right? So how is it that my meter stick doesn't push up with too much force? How does it know to push with just the right amount? Because it only pushes back with the amount that corresponds to the deforming. So the more I deform it, the more it pushes back. As soon as I start to take the deforming away, I don't see as much. So I'm going to do this right here. See if I can balance this out. So I've got my little Santa Pez right there. So think about how much deforming has happened here. Now, as soon as I start to lift up my book, the deforming starts to go away. And just like that, now I get enough deforming to only lift up on the Santa. If I place my book back down without trying to knock over Santa, okay, if I can lift it up quickly without making this thing wobble, okay, this thing is not thrown in the air because as soon as I take some of the weight off, it immediately starts to deform because the spring model suggests these atoms are already pushing back, trying to regain their shape. As soon as I take away some of that force, it's able to regain its shape. And as soon as it regains its shape, it isn't pushing back anymore. So that's how that concept works right there. So all of this relates to the deforming of a solid. Even if you can't see it, at a very small molecular level, you are going to see that those atoms are being smashed together. And the more I push, the more the atoms smash together, the more they respond with this support force out of a surface. And remember that support force is perpendicular to the surface. So it's not always just straight up. Most of our examples are straight up because usually we're dealing with a flat surface and we're setting things on top. But anytime you press into a solid surface and you don't rip or fall through it, you have an outward perpendicular force. And that is our normal force. And again, we use the spring model to help us understand and explain how it is that that model works, how it is that normal force works.